This Embryology Highlights screencast deals with musculoskeletal development of the trunk, limbs, and head. Beginning with the trunk region and skeletal muscles. Skeletal muscles of the trunk are broad and innervated by multiple spinal nerves. They can be categorized as epaxial muscles innervated by dorsal branches of spinal nerves, or hipaxial muscles innervated by ventral branches of spinal nerve. Epaxial muscles generally above the transverse processes of vertebrae. This image shows a dissection of a cat cadaver. The ribs are here, the thigh is here, and we have reflected the external abdominal oblique, which is reflected ventrally, exposing the rectus abdominis muscle. Here is the internal abdominal oblique muscle reflected dorsally, and that exposes the transversus abdominis muscle. You can see that all of these muscles are broad, and on the transversus abdominis we see spinal nerves. This is probably T11, T12, T13, L1, L2, L3 would be here. The broad muscles are innervated by multiple myotomes which overlap in forming these muscles, and each myotome brings its own innervation. This cartoon shows an earlier embryo on the left and an older embryo on the right. It shows that myotomes have migrated out to form an epimere and a hypomere. The epimere is innervated by dorsal branches of a spinal nerve. The hypomere is innervated by ventral branches. In time, then, the epimere is going to develop into the individual epaxial muscles of the trunk, and the hypomere is going to subdivide into the individual hipaxial muscles of the trunk. So the theme of muscle development then is for the single chunk of myotome to migrate out, combined with adjacent myotomes forming a regional mass. Large masses are going to subdivide into the individual muscles that one sees in the adult. This is a transverse section through a canine thorax. We can see a vertebra here with ribs articulating, and portions of ribs are evident elsewhere. It shows epaxial muscles. Here's one here. They are located above the transverse process of the vertebra, and then various hipaxial muscles that make up the wall of the thorax. The axial skeleton of the trunk is formed by sclerotomes. Sclerotomes give rise to vertebrae and ribs, and in the process of forming a vertebra, sclerotomes undergo a resegmentation so that each adult vertebra is actually formed by two adjacent sclerotomes. This shows earlier and later stages of vertebra and rib development. The vertebra and ribs develop endochondrally, and so we have a cartilage model first, and then these darker areas represent ossification that's going on within the cartilage model. And as you can see, there are multiple locations of ossification. This image diagrams the process by which sclerotomes give rise to vertebrae. And on the right here, we see a very early stage where this is a somite. At a later stage in development, the somite has given rise to a dermatome, a myotome, and a sclerotome. And the sclerotome mesenchyme has migrated to surround the neural tube. And then ultimately, the sclerotome forms a cartilage model of a vertebra, and that model undergoes ossification. Meanwhile, the ribs develop as processes off of the sclerotome vertebra. On the left, we have a schematic of a few segments. So we are sort of looking down at the neural tube, and coming off these segments of neural tube, we have a spinal nerve, the sclerotome and the myotome. So sort of this arrangement that you see over here. So this is the starting point where the nerve coming out and the sclerotome and the myotome all line up. What we want is this stage that you see down below, where the nerve comes out between two vertebrae and the muscles then go between vertebrae as well. And so muscles are going between vertebrae and nerves are passing between vertebrae. And so the vertebrae are off-shifted from the nerves and muscles, whereas they started out with the sclerotomes aligned with the nerves and muscles. And so the process of getting from that starting point to this point involves this. The sclerotomes, adjacent sclerotomes, form a continuous mass, so they lose their somite sclerotome segmentation. And then they happen to divide into dense and diffuse regions, each sclerotome. But the point is that this dense region from this sclerotome is going to ultimately merge with the diffuse region from the other sclerotome. And so we're going to end up with a vertebra formed by two adjacent sclerotomes. This image shows an actual embryo. We're looking at a ventral view of vertebral bodies. You can see that in the interzone between adjacent vertebral bodies, an intervertebral disc of fibrocartilage, annulus fibrosus, and nucleus pulposus, which comes from the notochord. These intervertebral discs then are going to separate the bodies of the vertebrae. And here we see condensations which are going to be cartilaginous ribs that will eventually ossify. Now, the first cervical vertebra, which is the atlas, has no body, and meanwhile, the second cervical vertebra, the axis, has a dens, a projection that comes off the cranial end of the vertebral body and extends into the area where the atlas is. This dens then is thought to be the embryonic body of the first vertebra that got attached to the second vertebra. Meanwhile, dens has to be bound down by ligaments because the spinal cord is located right here. And so this dens can lead to trouble if it projects up and impacts the spinal cord. Considering next limb development, we have skeletal muscles which come from the hypermere myotomes that form extensor and flexor masses, the appendicular skeleton, the bones of the limbs which are formed by endochondrally from local somatic mesoderm, and the skin, the dermis of which comes from dermatomes which migrate out as in bands. This cartoon shows a limb bud developing. We see extensor muscle mass and a flexor muscle mass, which are derived from the hypermere mass and are innervated by branches of the ventral branch of a spinal nerve. Eventually, these extensor mass will subdivide into the individual extensor muscles, and the flexor mass will subdivide into the individual flexor muscles. And so we have this muscle development theme of large chunks moving out into position and then subdividing into the smaller adult muscles. The development of a limb begins as a limb field, which grows out initially as a limb bud. And the first part of the bud is the more proximal part of the limb, and the last part of the bud to grow is the manus or pes. The limb bud consists of mesenchyme, which is induced to grow by an apical ridge of ectoderm, which induces growth of the limb bud. And then eventually the separate digits are produced not by outgrowths, but by degeneration in between the future digits. So this cartoon shows an early embryo and a later embryo. This early embryo is in the process of becoming cylindrical in shape. We can see that the lateral mesoderm undergoes cavitation, and so we have a somatic mesoderm, which is going to form body wall, and that and the ectoderm constitute a somatopleur. Here, at a later stage of development, we see the body wall, the somatopleur. Meanwhile, splanchnopleur has formed gut and mesenteries. It's this somatopleur, then, that is going to give rise to a limb. And what's going to happen first is that an area in this somatopleur is going to commit to forming a limb. And experimentally, if you move that area to someplace else, the limb will grow out from that other place. So initially, before any evidence of a limb formation, we have a commitment of these cells to becoming limb. This image shows photographs of actual embryos. This is an earlier embryo, and to the right is a later one. And so we can see the limb buds growing out from these fields that committed to forming limbs. And we see that the thoracic limb precedes the pelvic limb. And in this early stage, we just see an undifferentiated limb bud, but this first part that grows is going to become the more proximal part of the limb. Here we can see the manus, and so this is the proximal part of the limb that grew out first, and then this is a manus, which is growing secondarily, and here we see a pes. This is a tissue section of a limb bud. It's a lower power on the left and a higher power on the right. The mesenchyme content of the limb bud is colored yellow, and the apical ridge is colored red. Turns out that the apical ridge then induces the mesenchyme to grow, and in fact the mesenchyme induced the apical ridge to develop. So there's a mutual interaction here that promotes continued growth of the limb. This image shows the growth of a manus or pes at 3 different stages of development, from early to late. And it shows then that the individual digits grow not by outgrowths of the foot plate, but by degeneration, necrosis of the tissue in between. The last region we want to consider is the head. The head consists of a cranium, which develops in association with the head process, and then a face, which has to grow out later by pharyngeal arches. The skeletal muscle in the head comes from somites or semitomeres. The muscles are innervated by cranial nerves, and the bones of the skull are largely intramembranous, although some are formed endochondrally. This is a anterior view of a younger embryo and an older embryo. Initially, at this stage, we have a cranium formed in association with the head process, and the face is just beginning to grow via the upper and lower jaw, and a nose is beginning to grow. And here we see this lower jaw and the upper jaw and nose are here. And in the process of forming jaws, a mouth cavity is created. The face then grows separately from the cranium, and it grows by outgrowth of pharyngeal arches. This drawing shows 3 categories of bones of the skull. The bones of the face and the bones of the calvaria develop intramembranously within ectomesenchyme that comes from neural crest. So neural crest migrates to these regions, and the bones that it forms is intramembranous. Meanwhile, the bones at the base of the skull are formed by the most rostral somites, occipital somites. And so these bones are formed endochondrally from sclerotomes of those somites. This is a dorsal view of a fetal skull, and we see the bones of the calvaria and the bones of the face, which have developed intramembranously. The bones develop within fibrous tissue. Initially, there's a fontanelle, a soft spot, which eventually disappears as bone growth closes this and completely ossifies the calvaria. This shows that muscles of the head develop from myotomes that migrate into pharyngeal arches. Whatever those pharyngeal arches become then, that musculature then comes from these pharyngeal arches via the myotomes that migrated there. In addition, myotomes will migrate around the eye to form eye muscles and to the tongue. We will discuss the pharyngeal arch development when we discuss development of the head. By means of a summary, the pharyngeal arches receive ectomesenchyme from neural crest, and that gives rise to the connective tissue and bone. Meanwhile, myotomes come from semidomias and somites that migrate into pharyngeal arches, and each pharyngeal arch is innervated by a particular cranial nerve. So whatever that pharyngeal arch develops into, that cranial nerve will take care of that innervation. And here is a listing of what the main arches do. The fifth arch degenerates, and so fourth and sixth merge, and actually only the first three are evident in the mammalian embryo. In this drawing, the three pharyngeal arches that are visible are colored in. The first arch that's going to form the upper jaw and the lower jaw, and so it is already developing two processes. So this concludes this embryology highlight screencast that discuss musculoskeletal development of the trunk, limbs, and head.